students, today we'll study about a very interesting topic, and that topic is capacitor. So let us move quickly on to capacitor. We will go quite slow and then we'll do all the derivation. So let's start.
So what are capacitors? Capacitors are basically electrical devices which are used to store the electric charge. So the work of any capacitor is to store electric charge. So you can also call them as electric charge storage devices. And the symbol we use to represent the capacitor is like this, because here we have two plates. These two are conducting plates, and there is a voltage difference between these two plates. And the symbol we use to represent the capacitor is this. Here these two standing lines, they represent conducting plates. These are the conducting plates which are any metal. They are made up of metal, and these conducting plates are separated by a distance. This distance may be any media, this may be air or paper, but this should not be conducting. The medium which we are using to separate these two conducting plates should not be conducting, because in capacitors, so electric charges, they travel from low voltage towards high voltage. So there is a voltage difference maintained between these two conducting plates, and due to the transfer of these electric charges, and that transference is again due to the voltage difference, then they have a capacity to store the charge. This property or this capacity of storing the charge gives them the name capacitor, and hence we call these devices as capacitors, because they have a capacity to store the electric charge. So the word comes from the capacity and capacity of storing the charge, and this charge is electric charge. So at once when you hear the name capacitor, just relate it to the property of capacity of storing the charges. A good capacitor will have a high value of capacity of storing the charges, and it is denoted with the symbol C. C is the symbol for capacitance. Always relate this word capacitance to capacity. And once you relate with the capacity, then it is very easy to correlate with how these device works and what we can gain out of these devices. Right? So let us say that we want to show a capacitor. So the symbol is like we have two parallel plates, two conducting plates which are parallel to each other, and these two plates are separated by any distance. Here we have shown a distance between these two plates, and these are at different potential. Right? So there is a potential difference between them. Why we have kept the potential difference between them? Because we want the charge to be transferred, and in order to transfer the charge, we have a potential difference. So what we say that we have a system of two conducting plates which are separated by any medium, any insulating medium, and if we have a different charge, if we have a voltage difference between these plates, then we call this device as a capacitor. And sometimes instead of two plates, we use a single plate. We call it a single conductor capacitor, and we are calling it as a capacitor because the second plate we can assume at the infinity. One plate is present and the other one we can assume to be at infinity. So that is a single conducting plate capacitor or single plate capacitor. So if there is a potential difference, if the two charges, the charges plus Q and minus Q, then there is a voltage difference that will allow the charges to flow. And if the charge flow is there, some voltage is there. So if there is a potential difference, that means there is an electric field present in between these conducting plates. So let us say that the electric field is E, we are assuming. Then this electric field E will be directly proportional to the charge on these plates, because we have plus Q and minus Q. So the electric field in the region between the conductors, that is the insulating area, then the electric field in this area is proportional to the charge capital Q. and so it has a linear dependence on the charge q. So if the charge is doubled, the electric field also be doubled at that point. Has a linear proportion to the charge. So direct away, if we double the charge, then the electric field will also be doubled. Now to electric field, let us move on to the electrostatic potential. And the electrostatic potential is represented with the symbol capital V. And the formula for V is KQ over R. And if you want to go into the details of what is electrostatic potential, how it is developed, and how we got this formula, you can refer to my lectures, and the link is given below. But as for now, the electrostatic potential has a symbol V, and this is the formula we use to represent the electrostatic potential. So K is a constant here, Q is a charge, and R is the distance. So here we are keeping the distance constant. So you can say that V is also having a linear proportionality on the charge Q, right? Our V is linearly proportional to the charge Q present on the plate. And if you want to define this electrostatic potential in simple terms, so you can say that V is the work done per unit positive charge in taking a small test charge from conductor 2 to 1 against the field, right? The general definition is that if V is the work done per unit positive charge in taking a small test charge from infinity to any point, but here for the capacitor we are having two plates, so we can define it as V is the work done per unit positive charge in taking a small test charge from the conductor 2 to 1 against the field, right? So that is how we can define the electrostatic potential, and this electrostatic potential is directly proportional to the charge Q. As V has a linear dependence on the charge Q, so we can simply write down that if we take the ratio of Q upon V, then it will be a constant, and the constant pair we introduce is our capacitance C. So this simple linearity relation will give us a formula to calculate the capacitance. So Q upon V is a constant, and this constant is the capacitance. Or if you're using any device that is called as a capacitor, then the C is termed as the capacitance of that capacitor. So you can simply use the formula Q upon V is equal to C is equal to capacitance of a capacitor. That is the charge storage capability or charge storage capacity of a capacitor. So capacitors are very simple and very much scoring. Either if you're going for your 12 board exams or if you're going for any of the competitive exams, these are quite easy to understand and score good. So once the basic is clear to you, you have to just pay attention on the basic. Then capacitor is very easy. You can solve all the numericals, you can do all the derivations. Just stick to what we learn, just try to understand, make it clear in your mind, and then everything comes so easy. So now we know what is a capacitance. It is a charge storage capacity and is the ratio of charge Q to the electrostatic potential V. So the ratio of Q and V gives us the capacitance of any capacitor. If we come to unit of the capacitor, then if we use SI unit, then SI unit of capacitance is farad. How to remember this unit farad? Because it is in the name of the scientist Faraday. So let us remember very easily that the capacitance is measured in farad. And if you write down capacitance, use the simple formula C is equal to Q upon V, and the unit for capacitance is farad. Then you get the definition of farad. What is 1 farad? Q is always measured in coulomb. So Q gives us the charge, that is in coulomb, and V gives us the electrostatic potential, that is in volt. So if we take both as unity, we take the charge as 1 coulomb and we take the voltage as 1 volt. Then we will get the value of 1 farad. So what is 1 farad? We can define as 1 farad is 1 coulomb per volt. So if there is a potential difference of 1 volt between the plates and there is a transference of 1 coulomb of charge, then the capacitance of that capacitor is 1 farad. Okay, if there is a unit potential difference between the plates and a unit charge is transferred, then the capacitance is said to be a unit farad or 1 farad. So that gives us simply how you can calculate a farad. And symbol we can use, as I told you, that if it is the distance is fixed, then we take two parallel conducting plates and there is a distance between them, and in this distance we may have any insulating medium, we may have air, we may have water, we may have paper, or we may have any ceramic, but this should be insulating. That means it should not be a conducting medium. then we call this setup, we call this device as a capacitor. And here, because this distance is fixed, so we call it as a fixed capacitor. Here the capacitance is fixed, so this is called as a fixed capacitance capacitor. And if this distance is variable, that means we are having two conducting plates, but if the distance between these two variable, then we use a symbol like this. This insulating medium is variable, then we call this capacitor as variable capacitance capacitor. So now we know the definition of capacitance, we know the formula of capacitance, and we also know the unit of capacitance. So similarly, as coulomb is a very large unit for the charge, we always write it down in millicoulomb or microcoulomb. That millicoulomb is 10 to the power minus 3 or microcoulomb is 10 to the power minus 6 coulomb. Similarly, we do not use this farad because as this is a very large unit, so we use the unit as microfarad. Microfarad is 10 to the power minus 6 farad, or sometimes nanofarad. Nano is 10 to the power minus 9 farad, or we use picofarad. Picofarad is 10 to the power minus 12 farad. So whenever you are solving the numericals, you will find, because this farad is a very large unit, I'll tell you why this 1 farad is a very large unit. Obviously, we'll come to it, but for now you can say that this microfarad or nanofarad or picofarad is in use because this has practical values either as micro or nano or pico. So micro is 10 to the power minus 6, you have to remember. Nano is always 10 to the power minus 9, and pico is 10 to the power minus 12. So these are those small units of capacitance, which is in farad, micro, nano or pico. So just remember these values and then you can easily find out the capacitance. This 1 farad is very large a value. How much large is it? Because if you use a parallel plate capacitor, we get the capacitance as C is equal to epsilon naught A upon D, where the distance between two parallel plates of the capacitor, D, is very small than the area of the capacitor plates. Each plate is having the area A, so this A is having a value very large than the distance between the plates. So we want to calculate the capacitance as 1 farad. We want to get this capacitance as 1 farad. So what we want to do, this epsilon naught is a constant, that is a permittivity, and if we take this D is in denominator, so we can take it, if you want to get this capacitance as a large value, so we can take this D as a minimum value. So minimum value we can take it as a 1 centimeter, let us say, for the minimum value, and 1 centimeter means if you convert it into meter, that is 10 to the power minus 2 meter. That is the minimum distance we are taking between two parallel plates. Then epsilon is constant, D is we have taken, C we want to calculate as 1 farad, then A. How much should be the area of the parallel plates of the capacitor? So A comes out to be CD divided with epsilon naught. Let's put the value. C we simply need is 1 farad, and this distance we have kept very small as 1 centimeter or 10 to the power minus 2 meter, and epsilon naught is the permittivity of the free space, which has a value of 8.85 into 10 to the power minus 12 coulomb square upon Newton meter square. If you want to know more about permittivity, then go to my lectures. The reference is given here, where we study about electric flux. But as for now, this is the value 8.85 into 10 to the power minus 12 coulomb square over Newton meter square. So let us see what we get. Here we are having 10 to the power minus 12, and here we are having 10 to the power minus 2 and 10 to the power minus 12. So if it go upwards, then it will be 10 to the power plus 12. So this is equal to 1 upon 8.85 into 10 to the power plus 10. Or we can write it down as 10 divided by 8.85 to easy calculate into 10 to the power 9. So it is, we can take this value as around 1. So it comes out, roughly comes out to be 10 to the power 9 meters square. That should be the area of a single plate. Can you imagine how much large this area is? 10 to the power 9 meters square. So that is not a feasible value. This value is not feasible. If you take even this large value of the capacitor plate, then you will have the capacitance of 1 farad. So this is just to give you an idea of how large the unit farad is. That is why we use the small units, -6, -9 or -12. So if you want to make a capacitor of 1 farad capacitance, it is not feasible, it is not possible. Why is it not possible? Because if you take the minimum value of D and you do all the calculations, even then you get the value of area of the plate of the parallel plate capacitor is 10 to the power 9 meters square, which is very large a value. So that is not feasible to have this plate area. So that is why we say that 1 farad is a very large unit, and 1 farad is having impractical values. That is why we do not use such large units. So see how easily we have understood the capacitance. Now just remember the points and everything is very much clear in capacitance. Let us come to the first point, and if you remember these points, then capacitance will always be in your tips. No need to worry about the capacitance. The first point is, we just realized the relation that Q upon V is equal to C. The ratio of the charge to the electrostatic potential gives us the capacitance. And this is the magical formula. We have to always remember all the physics comes out of this formula only. So C is a constant which we call as the capacitance, and this is derived with Q upon V. Now, which capacitor will be a good capacitor? That capacitor will be a good capacitor which has a large value of C. Obviously, a capacitor which is having a good capacity, which has high capacity of charge storage, will be a good capacitor, right? So, if we need a good capacitor, we need a large value of C. You agree with me? Yes. Okay, fine. So if we need a large value of C, that means we are having a capacitor with large capacitance, and that is what we want from a device. So for large capacitance, if you see, if we want this value as large, go to the mathematical formula. If you want this value of C to be large, then this Q should have a large value, Q should have a high value. For C to be high, this should be high, and this should have a low value. That means if we want a large value of capacitance, then this charge should have a large value and this potential should have a low value, right? So for large value of C, charge Q is fixed, Q is the charge given to the plates. So V should be small. So what do we say? That V is small for a given Q. The value of Q is kept fixed. So if you are given with a value of Q, then V should be small for C to be large. What does it mean? That a capacitor can hold the charge, or a capacitor with high capacitance value hold a large amount of charge Q at a relatively small value of potential. What does it mean? That if we want this value of C to be high and this Q we kept as fixed, right? If you want to increase the C when Q is kept fixed, what you can do? You can simply reduce the value of P. So that is what we want to say. That if we want a capacitor with large capacitance that can hold a large amount of charge Q at a relatively small voltage. So that capacitor is a good capacitor which can hold a large amount of charge at a relatively small voltage. That means the voltage we are giving should be low, and if it is able to store more charge, then we call that capacitor as a good capacitor, or it has a high value of capacitance, large value of capacitance. That is our first one. Second is, if we come to the electric field, right? So what is E? E is equal to the difference in the electrostatic potential. See, we take 2 points, one is point A and the final point is point B. So if we are having 2 points A and B, then the electrostatic potential will be VB at any point and V at another point. So the difference of these two, VB minus VA, will be delta E. That will give us the electric field, right? So what is this? This is the potential difference. So high potential difference can give us strong electric field around the conductors. So if we need a high electric field around the conductors, then this potential difference should be large. This potential difference should be high. So high potential difference gives strong electric field around the conductors, which can, okay. So what we need to do? We need to keep the potential difference high if we want to increase the electric field. But what is the consequence of keeping the potential difference high or keeping the electric field high value? What happens that when we are having strong electric field around the conductors, then this strong field can ionize the surrounding air. Say we are taking capacitor and the insulating medium between two parallel plates is maybe air. It may be any insulating medium, say for example air. So if this electric field is very high value, then what happens? This can ionize the surrounding air and accelerate the charges so produced. If the electric field is very high, it will produce some charges. Then they will accelerate to the oppositely charged plate, because we are having positive Q and minus Q, plus Q or minus Q here. So this accelerate the charge to the oppositely charged plates and thereby neutralizing the charge on the capacitor plates. You get interesting? If there is an insulating medium, that is air, and high electric field is applied, that will ionize the air, and this air ions, positive ions will start moving towards the negative plates and negative ions will start moving towards the positive plates, and here there will be neutralization. So it can neutralize the charge on the capacitor plates. So that is an unwanted thing. So we can keep the electric field high, but that is a consequence. So we have to keep a mind on this also. Third point is that the maximum value of electric field. We can increase the electric field, but we know the consequence. So the maximum value of the electric field can be capped up to only that value that the medium in between the capacitor plates. What we keep usually, we usually keep the medium as dielectric medium. So here we keep the medium as a dielectric medium. If you want to know what is the dielectric medium, how the dielectric behaves in the, what is dielectric, what is so the medium we usually take between the capacitor plates is a dielectric medium. So whatever is the dielectric medium we are taking between these two capacitor plates, so that decides our maximum value of electric field. So the maximum value of electric field for any dielectric medium should be such that this value can withstand the breakdown. There is a breakdown, so that this value of E maximum, this should not exceed this condition of breakdown. So the dielectric medium which can withstand this maximum value E, that is known as the dielectric strength. So every dielectric medium has this dielectric strength. This is the strength of the dielectric medium to withstand the maximum value of electric field. So whatever is the dielectric strength of that particular dielectric medium, that decides the value of electric field E. Say for example, if we take air, that comes out to be around 3 into 10 to the power 6 volt per meter. So you can keep the maximum value of E to this. So whatever is the dielectric medium, the corresponding dielectric strength gives us the value of the maximum electric field we can utilize. What we need is a capacitor which has a high capacitance. So if we want a capacitor which is a high capacitance, that means it can store a large amount of charge and this charge should not leak out, then its capacitance should be high enough so that the potential difference, this is the potential difference, Okay, so that the potential difference and this potential difference decides the electric field. So this potential difference and this electric field E, they should not exceed the breakdown limit. Fine. So if we need a capacitor which can store a large amount of charge without leaking, its capacitance should be high enough so that the potential difference and the electric field do not exceed the breakdown limit. Again, we use the relation C is equal to Q upon B. Q we can keep fixed, and this potential difference should be such that, because this potential decides the value of capacitance, so this potential difference value or this electrostatic potential value we have to keep such that it is below the breakdown limit, then we can keep this capacitance high. So these are the four simple points we have to remember whenever we are dealing with any kind of situation of the capacitance, and both are based on the easy formula C is equal to Q upon V. So you have to play with three quantities. Either you can keep this fixed, or you can put all the limitations on this, and this in turn will put the limit on the electric field. So you have to keep this in the breakdown limit, and then you can choose such a capacitor which can store a high amount of charge at this low value of voltage, keeping in mind all these 4 points. So that decides the capacitance of a capacitor. So a very simple type of capacitor is a parallel plate capacitor. Here we take two conducting plates. So you can see this is plate 1 and this is plate 2. These are two conducting plates which are parallel to each other. So we call this as a parallel plate capacitor. And the symbol we use for capacitor, you know, this is the symbol we use. That means we have two conducting plates which are parallel to each other, and there is some difference between them. So here you can see that these conducting plates are kept at some distance. This distance we have taken as small d. So small d is the fixed distance between these two plates. So this setup we call as capacitor. And there is also a potential difference between these two. Here this plate 1 is given with a positive charge, and say plate 2 which is given with a negative charge. So this is a continuous charge distribution. So all these charges they collect on the surface of these conductors. So here we are having positive polarity, and on the second place we are having negative polarity. So these are at the surface of the conductor, because inside the conductor the electric field is 0. So we have the charges only at the surface of the conductor. So there is a potential difference. So there is a charge transfer from this side to this side. So this we have shown as the direction of electric field. So what is the direction of our electric field? So these arrows in blue, these shows the direction of our electric field E. And since there is a continuous charge distribution, then the surface charge density is represented with the symbol sigma. So here we will have a positive surface charge density plus sigma, and on the second place we have minus sigma. So the second plate has a negative surface charge density, and we know that sigma is given as, because the surface charge density, this is charge per unit area. So we can simply write down wherever we have to write down the charge Q, we can simply write it as sigma A. So let us move. So we take two large plane parallel conducting plates separated by vacuum. The medium here we have taken as that there is a vacuum, no air, nothing. So here the dielectric medium we have taken as a vacuum is the medium between these two parallel plates of this capacitor, and the area of each plate is denoted with the symbol capital A. So both plates have similar value of A, and the condition we are taking here that the distance between these two parallel plates, this distance is very smaller in comparison to the area of these plates. These plates are having a large area in comparison to the distance between them. So this is the condition we are imposing when we are doing this derivation. So if we are having plus sigma surface charge density and minus sigma charge density, then that will give us the value of Q. So you can say that we can easily write down here the charge is plus Q and here the charge is minus Q. So that completes us the picture of our parallel plate capacitor. Now the only thing we have to do is to calculate the electric field, because since there is a potential difference, then there will be an electric field. So we want to calculate the electric field, and in order to calculate the electric field, we have to take this capacitor into the consideration. So you can say that before the first plate, which we have given with the area first, that is the custom representation of this. So we have taken it according to the custom. So this is the first region we have chosen, and the second region is between two parallel plates. So this is the second region, and below the second plate or after the second plate we have the region 3. So we can divide it into 3 regions. First is just before the parallel plate having the charge plus q, second is between these two plus q and minus q charge plate, and third is after this charge plate of having minus q charge. So in these 3 regions we want to calculate the electric field. So let us move into this region one by one. So electric field in region 1. Let us first move to the first region, and in this region, because we know that there is a potential difference, plus charge here, minus charge here, so the total electric field will be the sum of these two, and we know that whenever we are having a large conducting surface having the surface charge density at sigma, then the electric field is given by the symbol, then we know that the electric field E is given by the formula E is equal to sigma upon 2 epsilon naught. This we are taking already, we are not deriving this relation here, but if you want to go to this derivation, then I have given the link where we calculate the electric field using the application of Gauss law. You can apply the Gauss law, you can easily calculate this field. The link is given below. You can quickly catch up that lecture and find out how we got this E is equal to sigma upon 2 epsilon naught. But for now we are taking that this is producing the electric field of sigma upon 2 epsilon naught. So first the electric field will be due to the surface charge density plus sigma, and then due to the minus sigma. So plus sigma will give us the value of sigma upon 2 epsilon naught, that is due to the first plate, and the second plate we will have the value of minus sigma upon 2 epsilon naught. So if you see, these are equal in magnitude and the sign is different, so both of them cancels out and give us the resultant field as 0 in the region 1. So in the region 1, due to these two conducting plates, the total electric field comes out to be 0. As this is before the first plate, then first we can go to after the second plate and then we can calculate in between. So we are skipping our region 2 now, we will do it after this region 3. So next is electric field in region 3. In region 3, if we also see that the electric field will be the sum of electric field due to plus sigma and electric field due to minus sigma. So we can simply write it as that due to plus sigma or due to the charge plus q, it is sigma upon 2 epsilon naught, and due to minus sigma, it is sigma upon 2 epsilon naught with a negative sign. Again, both are equal in magnitude and different in sign. So the net electric field comes out to be 0 in the region 3. So in the region 1 and region 3, that means here in this region or in this region, the electric field, the net electric field comes out to be 0. So we are not worried about whenever you are using a parallel plate capacitor, do not ever worry about the electric field in these two regions. If you are having the similar surface charge density with opposite sign. And now we come to the important region, that is the electric field in region 2. So what is the electric field in second region? So due to the charge plus q, we will have the direction of electric field like this. So E will give us the value of E is equal to due to plus sigma, it is sigma upon 2 epsilon naught. And due to minus sigma, it is obviously minus sigma upon 2 epsilon naught due to minus sigma, but these two are acting in the opposite direction. So again, we will have a minus here. And if you want to know how we calculate the direction of electric field, then you can quickly move on to a lecture on electric field. The link I have given below, but here for now you can say that these two are acting in the opposite direction. So this is the opposite direction, and this is due to the charge density, that minus is there, and this is the sign of direction that we have taken the sigma. So this minus minus will give us a plus. So we will get the total electric field as sigma upon 2 epsilon naught, and 2 minus will make a plus sigma upon 2 epsilon naught. So both of these electric fields, they will add up in the region between the parallel plates. That is a thumb rule, that in the region second, these two electric fields, they add up, and they add up to give the total electric field as half sigma upon epsilon naught, per half sigma upon epsilon naught will give a full sigma upon epsilon naught. So what we get in the region 2 is E is equal to sigma upon epsilon naught. This is the electric field due to two parallel plates of the capacitor. So E is equal to sigma upon epsilon naught. And what is sigma? Sigma is the surface charge density. So sigma is equal to Q upon A. So either you can write down the electric field in this value, or if you can replace sigma with Q upon A, then you can also write down in terms of Q. So put sigma as Q upon A. Sigma is replaced by Q upon epsilon naught is already there, A. So E is equal to Q upon epsilon naught A in terms of the charge and in terms of the area of this parallel plates. We can write it down as this. Now if you see the electric field is directed from positive plates towards the negative plates. So E is uniform throughout the plate. We say that the electric field is uniform throughout this region 2. It is directed from plus to minus, and it has the same magnitude at each point. So within two plates of the parallel plate capacitor, the electric field is same and E is uniform throughout. So electric field we have calculated, and if we want to calculate the potential, if we know the electric field, we can easily calculate the potential. So the relation is E is equal to minus delta upon delta L of V, or in general, if you write down E is equal to minus del of V, this is the relation between these two. So that if you know the potential, you can calculate the electric field. But inversely, if we know the electric field, then we can calculate the potential by simply integrating it. Now the relation between the electric field E and electrostatic potential is that if you differentiate it with respect to V, and the relation between E and V is that if you differentiate the V with respect to R, then you will have the electric field, or inversely, if you want to calculate the electrostatic potential with the known value of electric field, then you can simply integrate it with respect to dr. So V is equal to E dot dr. So here we are calculating the value. So if you integrate it for this value, then V is equal to E, and this total distance the charges are traveling is d. So this is V is equal to E dot d. And if you put the value of E, then what is the value of E? E is equal to Q upon epsilon naught A. Then putting the value of E as Q upon epsilon naught A, and this is multiplied with d. So the electrostatic potential is V, capital V is equal to Q d upon epsilon naught A. Here Q is the charge on each plate, d is the small distance between these two plates, epsilon naught is the permittivity of the medium, and here we have taken a vacuum, so this is epsilon naught, and A is the area of each plate, we got it. So, and now the capacitance we have to calculate. Finally, what we want to go, because we are having a parallel plate capacitor, so we want to calculate the capacitance C of this parallel plate capacitor. and the thumb rule, C is equal to Q upon V. Never forget, this whole story lies here only in this small formula. C is equal to Q upon V. Now we know the value of V, so we can simply put the value of V here. So Q remains as such, and the value of V we got is QD upon epsilon naught A. So Q cancels out with this Q, so that gives us the value of C is equal to epsilon naught A divided with D. And this is for a parallel plate capacitor, where the two plates are having, each is having the area A, and both of them are separated with the distance small d. So this d we have taken as very small than A. So C is equal to capacitance of this parallel plate capacitor is always epsilon naught A upon D. Always remember this formula, and if you remember the formula using Gauss law for electric field, then you can quickly calculate, or you can easily remember the value of E. Once E is known, then V is very easy to calculate. Within seconds you can get the value of V, and then you have to do Q upon V. So whatever the derivation you are doing, finally we have to use the expression Q upon V. So Q is there, and you have to reach up to the electrostatic potential, and this electrostatic potential you can easily get by integrating E. So first find out E, integrate it, get V, and put the value in C is equal to Q upon V, and that will ultimately give you the value of C. The only hierarchy you have to keep in mind is first go for E, integrate E, V get V, put the value of V in C is equal to Q upon V, and get the value of C, right? So that is what we have done in this. To calculate the electric field, we have taken the three regions. First region 0, third region 0, second region, both add up, we get the value of E, we integrate it with respect to V, and we put the value of V in C is equal to Q upon V, and we have the final value of C. So if you remember this order we have to do, you will never forget it. So that is the easiest way to remember to do the derivation. And even if you want to remember the formula, then it is easy to remember E and easy to remember C, but in case if you want to calculate, you can easy do. But if you want to calculate, you can calculate it very easily. Now, one more thing we want to do to this parallel plate capacitor, because here we have taken this medium as a vacuum. Here we have taken a medium as vacuum, so we are using the permittivity as epsilon naught. But what do? We introduce a dielectric medium into this parallel plate capacitor. Then how the dielectric medium affects the capacitance of this parallel plate capacitor. So we keep our system as same. We take two large plates of area A, they are separated by a distance small d, and the charges there are plus q and minus q. Charge are distributed in terms of continuous charge distribution, having the surface charge density plus sigma minus sigma, and sigma will give you the value of q. So sigma is equal to q upon A, or q you can simply get by multiplying the surface charge density with the surface, that is A, so that will give you the value of q. So everything we are keeping the same. The only thing we are using, that is we are replacing our vacuum with the dielectric medium. Then let's see what happens. Okay, so let us know the terms we got from the previous derivation for a vacuum. What we got first was that E in the second region was equal to sigma upon epsilon naught, that is between two plates. Then we calculated this V electrostatic potential, that was equal to electric field. After integrating, we get the distance at D. So V is equal to E into D, and then we use C is equal to Q upon this V. And after putting the value of Q, we got it as epsilon naught A upon D. This is all we have done already. We are now much familiar with it. Now we replace this vacuum with a dielectric medium. So when we replace this with a dielectric medium, then what happens? Initially our electric field was sigma upon epsilon naught, but whenever we keep this any dielectric, in the presence of external electric field, then there are some polarized charge. The link I have given below for the dielectrics in external medium. So here we are keeping this dielectric in the external medium. So there are, what happens in the dielectrics, let me tell you in the short, because if you want to go to the detail, yes, you can refer to my lecture, but here I can quickly tell you that if you are having any dielectric and this dielectric you have kept in any external, say this is a dielectric slab and this you have kept in external electric field, say this is the direction of electric field, then what happens, because this is a dielectric, it may be consisting of polar or non-polar molecules, but in the presence of external field it has some induced dipole moment or it gets polarized, that all the dipole moments are aligned in this direction along the direction of electric field. So there is a polarization here and there are some polarized charge density here, sigma p with negative sign and this plus sigma p, right? So this polarized charge density, it tries to opposes this externally applied electric field. So there is an effect of this surface charge density which try to reduce the electric field. So what happens if you are keeping any dielectric, then the electric field E is equal to sigma upon epsilon naught is reduced with the amount of polarized charge density. This charge density arises due to the polarization of these molecules, these dipole molecules, and this is a dielectric. Whenever it is an external electric field, then it causes the sigma p. So it is reduced from the amount sigma to sigma minus sigma p, and epsilon naught remains the same. E is equal to sigma minus sigma p upon epsilon naught, and then V is equal to E into D, that is the electric field multiplied with the distance between the two parallel plates of the capacitor. So put the value of E as such, sigma upon epsilon naught is replaced by sigma minus sigma p upon epsilon naught, and then it is multiplied with the distance d. And if the dielectric is linear dielectric, if the dielectric medium we have inserted between the parallel plates of the capacitor, that dielectric is a linear dielectric. What is a linear dielectric? Go to the same lecture quickly and find out what are linear dielectrics and how they behave. So, but as for now, you can say that for a linear dielectric, this polarized charge density is directly proportional to the electric field. So that is a linear relation, that whatever is the polarized charge density, it has a linear dependence on the external applied electric field. So that is the linear dielectrics, that means the sigma p will be directly linearly proportional to E. Or you can say to the external applied electric field. So let us say that the external applied electric field is denoted with E naught. So all this previous derivation, we say this is E naught here and this is V naught here, because this is in the absence of dielectric. And what we got is C naught, right? And now we are getting is E, that is E into D in the presence of dielectrics, and these are in the absence of dielectrics. So whatever is the polarized charge density is proportional to the electric field, that is our externally applied electric field when there was no dielectric medium. So sigma p is proportional to E naught. Sigma p is proportional to E naught, and here we can see that sigma is also proportional to E naught. So we can say that sigma is proportional to sigma minus sigma p, right? Our discharge density sigma is also proportional to sigma minus sigma p. And to remove this proportionality sign, we introduce a constant. If you put equal to sign, then let us say this constant is k, and k sigma minus sigma p. We have removed this proportionality sign with the constant k. What is k? That is a constant of dielectrics. This is a constant characteristic of dielectrics, and its value is always greater than 1. It has a positive value and that value is always greater than 1. This is a constant characteristic of the dielectrics. Or we can say that sigma minus sigma p, if we calculate, then this is equal to sigma divided with this constant K. So now if we calculate the electrostatic potential V, then V comes out to be E into D. So put the value of E. So the value of V, here we can see, here the value of V is sigma minus sigma P upon epsilon naught into D. And sigma minus sigma P is equal to sigma upon K. So here we can substitute with sigma minus sigma P with sigma upon K. And epsilon naught is also there and D is also there. So this is sigma D upon K epsilon naught. And sigma has the value of Q upon A because the surface charge and C charge per unit area. So this can also be replaced. If we write it down the sigma in terms of Q, now this is Q over A or Q upon A. So this is equal to Q upon A and this is K epsilon naught. Right? Here we have substituted the sigma as Q upon A. Now we have got the value of E, we got the value of V. Now what are we going to calculate? Finally, we want to calculate the capacitance using our magic formula C is equal to Q upon V. Because whole of the story of the capacitance lies in this formula only. C is equal to Q upon V. If you remember this formula, that means you remember all the magic behind this formula. C is equal to Q upon V. Now we have the value of V. So keep Q as such. Now put the value of V. This is QD upon epsilon naught Ka. So Q cancels out with this and we have the value of C as epsilon naught K upon D. This is the value of capacitance we are getting for a parallel plate capacitor when there is a dielectric medium between them. Now, what is this epsilon naught K? K I told you is a constant for the dielectrics which has a value always greater than 1. Then here we call this the multiplication of epsilon naught into K is equal to epsilon, which is the permittivity of the medium. Epsilon naught is the permittivity of the free space or vacuum and this is the permittivity of the medium. So if we calculate this constant K here, then it is epsilon upon epsilon naught. That is the ratio of permittivity. The ratio of permittivity of any medium to the ratio of permittivity of the vacuum. So we call this as relative permittivity, or it is called as the dielectric constant of the substance. I am repeating once again that this K is equal to epsilon upon epsilon naught is known as the relative permittivity or the dielectric constant of the substance. Now if we go to the vacuum, when there was vacuum between these two, then initial our capacitance were epsilon naught A upon D, and when we introduce the dielectric medium, then we denoted the capacitance with simple C, and that we got is epsilon naught Ka upon D. So the only thing that is introduced is the dielectric constant of the substance. So if we take these two ratio, then the value of K comes out to be as such. K is the ratio of C to the C naught. That means the capacitance in presence of the dielectric medium and the capacitance in the presence of vacuum, that is the absence of the dielectric medium, and that will give us the value of constant, or these two capacitance vary only by the value of this K dielectric constant of the dielectric. So what we can say that the dielectric constant of a substance is the factor which is always greater than 1 by which the capacitance increases from its vacuum value. Here K is multiplied whenever we are calculating the capacitance, then K is multiplied to this expression. Our earlier expression in the vacuum was epsilon naught A upon D, and when we introduce this dielectric, it is epsilon naught A upon D multiplied with K. So whenever we introduce any dielectric medium, the capacitance increases from its vacuum value by the amount of K. So when we introduce any dielectric medium, simply the capacitance is multiplied with the dielectric constant of that medium, and this dielectric constant is always having the value greater than 1. That means the capacitance increases. For any capacitor, the capacitance increases with the amount of the dielectric constant. So the capacitance now has a greater value in presence of dielectric in comparison to the capacitance in the presence of vacuum. So that is why we introduce a dielectric medium into a parallel plate capacitor so as to increase its capacitance.
So that's all for today. If you like this lecture, then like and share and subscribe to our channel Physics Class so that you get notifications for more such lectures. Thank you.